It took me a while when I was working through all this last fall to figure it all out too. All right. This one we're doing the hypothesis test for the difference of population means, a paired comparison. So it says here a personal computer manufacturer is interested in comparing assembly times for 2 keyboard assembly processes. Assembly times can vary considerably from worker to worker, and the company decides to eliminate this effect by selecting a random sample of 8 workers and timing each worker on each assembly process. Half the workers are chosen at random to be used for process 1 first, the rest process 2 first. Each worker in each process, the assembly time in minutes is recorded as shown in table 1. So for worker 1, process 1 took 33 minutes, process 2 took 30 minutes. The difference between process 1 and 2 was 3 minutes, and they filled out the table. Based on these data, can we conclude at a 0.5 level of significance that the mean assembly times for the 2 processes differ? Answer this question by performing a hypothesis test regarding U sub D, which is the difference, the population mean difference in assembly times for the 2 processes. Assuming that this population of differences, process 1 minus process 2, is normally distributed. So here for my null, I'm going to use U sub D. For the null, we always have the equal. So I'm going to say that the difference is equal to 0 if there's really no difference, right? There's no difference, the difference would be equal to 0. If there is a difference, it is not equal to 0. On this one, we are going to do the t-test when we compare these 2 things. And when we do the t-test, we have to have our degree of freedom. Our degree of freedom, again, is n minus 1. How many people did they survey? How many workers do they have? 8. So n is equal to 8, so n minus 1, going to be 7 for the degree of freedom, right? On our t-test, the degree of freedom is always n minus 1. So, we are going to then use this crazy formula, again, for our test statistic. For our test statistic, we are going to do what they call d bar minus u sub d, which again in this case is always going to be 0. Just like on that other one, the difference is going to be 0 if there are no difference. So we really don't have to do much calculating there. And then we're going to have S sub d for our standard deviation over the square root of n. So first thing we need to know is, what in the heck is d bar? D bar is the mean of your differences. So like on that previous one where they gave us that table, we have to find the average of the differences. So we've got to add up the values in this column and then divide by 8. So add them up first, and then it's going to be divided by 8 since there's 8 numbers there. So you're going to do 3 plus 10 plus 0 plus 15 plus negative 11 plus 11 plus 8 plus 21 and find that sum up there on the top. $57 yet? For some reason I didn't write it down, but 57 divided by 8 then is going to be what the mean of our differences are. If you take 57 divided by 8, what do you get? 7.125. Okay, that's the right number. 7.125. All right. Did I use my calculator on this one? I'm trying to see if they gave me a standard deviation. No, I did use the calculation. This is the standard deviation of my differences. On this problem, they didn't just give it to me. So I either have to use that great big long formula for standard deviation or use our statistics on our calculator. We could have found the mean a little, since we have to do both of them. We probably should have just used our calculator for both of them. So let's just go ahead and grab our calculator. Under the stats in list 1, we're going to enter in this data because we probably don't want to have to do the standard deviation formula since it's that great big long formula. So stat 1 to edit, put in those values from the table. That'll just make it a little easier. 3, 10.
Or the differences?
The differences, yep, of the differences. That's the one we're doing. So do your differences in list 1. So stat 1 to edit, put it in L1.
What is to sort it?
And then you don't need to sort it because we're just going to do the calculation. You could if you wanted to, but we're just going to do stat and calculate. Remember doing that, going over to calc, and then doing 1 to do our 1 variable statistics. And we want to do the 1 variable statistics on list 1. Your mean, which is your X bar on your calculator, should be the 7.125 we already figured out doing the long way, doing it the manual way. Standard deviation, if you look on there, you want the one with the S. What do you get for your value for your standard deviation?
For the X?
Yep.
I don't know if that's right. Did I do that right?
9.8, let's see, yeah, 9.819. Yep, that looks like it's the right one. So see the S there, S sub X on that, on a calculator? So you should get 9.891. 9.819.
Bar?
Variable. Yep, 1 variable statistic you have to do. 119. Got it down the right way. 9.819. So you do your 1 variable statistics on list 1 like we did hopefully a bunch of times by now. Alright, that way we don't have to use the formula for standard deviation. The mean formula isn't easy enough to do, but when they don't give you the standard deviation, that's a pain, and that formula is. So now that we know those numbers, we are going to do the 7.125 divided by the 9.819 over the square root of n was 8. There were 8 people that they were comparing. And again, when you figure out that answer, you're going to round to 3 decimal places. Yep. 2.052 is what you should be coming up with. So that's the value of our test statistic. We are going to do the critical value. When we do the critical value, that's always when we have the variable subscript. So in this case, since we're doing the t-test, we're going to do t sub something. Now in this case again, since we have an equal and a not equal, what we're doing that two-tailed test, right? And so we have to divide that by 2. If it's a one-tailed test, we'd use that number, but since it's a two-tailed test, I'm going to take my 0.05 and divide it by 2. And so if I do that, I'm going to get 0.025, right? So t sub 0.025 with a degree of freedom of 7. So whenever it's an equal and a not equal, it's a two-tailed test. We're going to divide that by 2 because we're figuring out each end separately. If I punch that into the Alex calculator, t sub 0.025 with the degree of freedom of 7, we get what number? 2.365, which means this side is negative 2.365. It's going to be between those two numbers. So negative 2.365 and positive 2.365 are going to be our critical values. When we do the critical value, the null is in the middle, the alternative ones are on the end. We are checking in which one of those 3 sections does positive 2.052 fall. Is it on either end or is it in the middle of those 2 numbers? It's in the middle, right? So 2.052 would fall between those 2 quick critical values. That means we're in the section where we're going to accept the null. The null is the true statement. That means the other one is not true. And so our question says, at the 0.5 level, can the company conclude that the mean assembly times for the 2 processes differ? Can we say they differ? No, we can't say they differ because we're saying they are the same. They're equal, right? They're either equal or they differ. We're saying the differ is not true. So no, we can't say that they differ. We're saying they're the same. We're saying they're equal. So number 5, can I get the bottom in there? Kind of. I'm just going to set it right there and read off my paper. Number 5, same thing. We are just going to use our calculator to do the mean and the standard deviation because on these ones they're not going to give them to you. So in list 1 you can start typing that in if you'd like. It says a personal computer manufacturer is interested in comparing the assembly times for the 2 keyboard assembly processes. Process 1 is the standard process used for several years. Process 2 is an updated process, hoped to bring a decrease in assembly time. Assembly times can vary considerably from worker to worker, and the company decides to eliminate this effect by selecting a random sample of 12 workers and times on each worker for the assembly process. Half the workers are chosen at random to do process 1 first, the rest do process 2 first. For each worker, each process, the assembly time in minutes is recorded in Table 1. Based on the data, can the company conclude at a 0.10 level of significance that the mean assembly time for process 1 exceeds that of process 2? So, this one wants to know if process 1 exceeds process 2 instead of saying the difference. If something exceeds something, it means that it's greater than, right? The word exceeds means greater than. Since this is a greater than, that's going to be my alternative hypothesis because my null always has to have the equal. So here, U sub D either is going to be, in this case I'm going to do the bottom one first, the greater than 0. It exceeds it, which means my other one, my D is kind of big on those. It's supposed to be a subscript. My other one then, for my null, since this is a greater than, would be less than or equal to, because the null always has to have the equal to one, right? So if it exceeds, I'm doing greater than 0. If it doesn't exceed, the difference is less than or equal to 0. So in order to do our formula, we have to find the mean of the differences and the standard deviation of the differences. And so in your calculator, in list 1, if you haven't already, put all those numbers into list 1. And then we're going to calculate the one variable statistics. So your mean, again, is just going to be the x bar. Your standard deviation is going to be the s of x on your calculator.
The 12.104.
For which one?
The S.
The standard deviation, 12.104. The mean, again, we can just use it off the calculator instead of figuring it out the long way like we did last time. The x bar is,
X bar is 2.167.
whoops, 167. 2.167. Yep. If you really wanted to, you could add all those up and divide by 12, and you should get the same number. But since we're doing our standard deviation, we could just as well use the calculator for the other number. All right. So our formula then, when we did our formula, we did the 2.167. How come I don't want to write the 1 today? 2.167, which is the mean of our differences, over the 12.104, which is the standard deviation of our differences, divided by the square root of n. In this case, n is 12. We had 12 workers or 12 people in our table, right? Oops, I forgot to do my test. We'll put that in there after we do the value of our test statistic. We'll just go out of order. So when we divide that out, 2.167 divided by 12.104 divided by the square root of 12.
.620.
0.6, whoops. Now I'm writing the answer in the wrong spot. 0.620. I skipped over the type of test statistic. The type of test statistic that we're doing on this one is our t-test, right? With a degree of freedom of, what is going to be the degree of freedom? 11. N minus 1, the degree of freedom, so 12 minus 1 is 11. We need to know that in order to calculate our critical value. On our critical value here, this time we are doing, does it exceed, is it greater than? We're just doing a one-tailed test and not a two-tailed test. So when we do our critical value, we don't have to divide by 2. We're just going to use the 10% level of significance. So we're going to do t sub 0.10 with a degree of freedom of 11. And so on our calculator, when we put that one in, we get 1.363. 1.363. So 1.363 is our dividing part. 1.363. The greater than is my H1, my null. The less than or equal to would be on the other side then, right? Since my difference is greater than 0 is my alternative hypothesis. So now what I'm checking is, does my test value fall on the left side or on the right side of that critical value? On the left side. It's in this section right here, right? It's smaller. That's my 0.620. That was my test value, which means since it falls on the left side, I'm going to accept that the null is true. This is my true statement. This one is not true. So, at a 0.1 level, can the company conclude that the mean assembly time for process 1 exceeds that of process 2? The exceed was the greater than. Can we say that's true? No, we can't, right? That was the not true statement. Can we say that it's true? No, I don't know why that has a yes, yes, and a no, no, but no, we can't say that's true. That was our not true statement, the greater than. Number 6. Again, if you want to get typing those in so that we can do our statistics, go ahead and put those in list 1. It says the owner of a chain of mini markets wants to compare the sales performances of 2 of her stores, store 1 and store 2. Sales can vary considerably depending on the day of the week and the season of the year, so she decides to eliminate such effects by making sure to record each store's sales on the same sample of days. After choosing a random sample of 12 days, she records the sales in dollars for each of the stores and the days shown in the table. Based on these data, can the owner conclude at a 0.5 level of significance that the mean daily sales of the 2 stores differ? So this is like problem number 4 was, where they differed, right? So if they differ, we're going to say either my U sub D is equal to 0 or U sub D is not equal to 0. So here we're doing one of those two-tailed tests. Either it's in the middle or it's on the 2 ends, right? Type of test statistic. We know we're doing the t-test. We have to have our degree of freedom. What is our degree of freedom going to be? 11. The degree of freedom is always n minus 1. N is 12 days. So degree of freedom is going to be 12 minus 1, which is 11. Now we can compute the value of our test statistic after we find our statistics here. So we need the mean of the difference and the standard deviation of the difference by doing our 1 variable statistics on that list of data. So in your calculator, in list 1, if you have all that data in, then stat, calculate 1 variable statistics so that we have our numbers that we need for the problem. So we're putting in all these numbers here from the difference column. So we hit stat 1, and then we put our list in list 1, and then we do stat and go over and calculate to do the 1 variable statistics.
So now you do this right?
What did we get? Oops, wait a minute. That doesn't look like we got the right numbers there. Let's go back to your list. Hit stat 1 for me. All right, we got 150, negative 48, 143, 231, 146, 236, negative 72, 244, 321, 75, and we should have a 60 on the end. Oh, we missed the 60. Enter that in. Now let's try it. So stat, go over to calculate, and 1 for 1 variable statistics, or just enter it. And enter through that. There, that looks better. Just forgot the bottom number. You maybe didn't hit enter on it.
Yeah.
All right, so we get 124 point, I don't know why I carried that out so far. Does it tell me 3? So I'm going to do 147 then to go to 3 decimal places, right?
Is it, did I do?
Whoops. Man, I just keep switching numbers today. 124.417. How about that? That look better?
Yeah.
Okay. And for my standard deviation, we would have
123.1. 0?
Yep. So the standard on here, your mean is the x bar, your standard deviation is the S of x. That's your sample standard deviation. All right, we now can throw those into the formula. So in the formula, we have d bar on the top over S sub d divided by the square root of n. So we're going to have our 124.417 divided by our 123.180 over the square root of 12. 12 was the number in our sample, right?
$3.499.
3.499. 3.499 is the value of our test statistic. We need to find our critical value. When we do the critical value, that's the T sub, right? Since we're doing a two-tailed test, we have to divide our significant level of significance by 2, right? 0.05 divided by 2 would give me 0.025. So we're going to do T sub 0.025 with a degree of freedom of 11. Whenever we have the two-tailed test, we're going to divide that by 2. So this side is 2.201. This side would be negative 2.201. So negative 2.201 to positive 2.201. And then, of course, the last part, at the 0.5 level, can the owner conclude that the mean daily sales of the two stores differ? So we want to figure out our test value. Where does our test value fall? If it's in the middle, we're going to accept the null. If it's on one of the two ends, we're going to accept the alternative. Where would 3.499 fall?
On the right.
On the way in section over here, right? 3.499. That means that the null, or that we're going to accept the alternative hypothesis that the null is the one that's not true. So this one's not true. This one is our true statement. Can we conclude that they differ?
Yeah.
Yes, they do differ. They're not equal. So yes, we're saying the not equal is true. So yes, they do differ.